Hello, hello, hello. Where's my hellos? Let's get a hello here. Hello, again, no hello, nothing, no love. Hello, thank you, Kaya. That's triple points for Kaya. See that she got. There's going to be a portal for not just hellos, but for love. I just got the. All right, hello, Kaya. Thank you. Hello, and I'm kidding, obviously. Hello, Ariana. Oops, sorry. Now everybody's okay. Hello, Ariana. Good afternoon, Yaneli, and thank you for the avatar or the picture. Good afternoon, Genesis. Good afternoon, Gabriella. Hello, Erica. Good afternoon, Samantha. Awesome, awesome. Now we're talking. Good afternoon, Sydney. Awesome, awesome. Um, Remember again, the whole purpose of all these hellos and everything, besides like boring you to tears on the videos when you watch them, is that it helps to break the ice so that if you have questions, you feel free to ask them right away. Because more and more I'm going to forget to ask you to ask me. I'm just going to roll. So yes, okay. So good afternoon, Sydney, and good afternoon, Brian and Matthew. If I didn't, okay. So again, if you have any question about anything, raise it now. You're welcome to raise it now. It's not an interruption. It is the curriculum. But if not, I'm gonna no. So no first one. Okay. Good afternoon, Sydney. If I didn't just say that, sorry. But I'm assuming that we're more and more clear on what's going on. So I'm gonna move forward in a moment. What we're gonna do today is let more people in. What we're gonna do today is today I'm going to try to show you, I am going to show you the point of the discussion that you had yesterday. Like it was a free form discussion in a way yesterday based on a seemingly hypothetical good afternoon, Emanuela. Thank you. Um, Yesterday's activity, the train of thought seems like a hypothetical, weird left turn from the course material. But today I want to show you why it isn't, why it actually means something. So that's what we're gonna do. So the board, oops, sorry, my bad. Sorry, hold on. Okay. So the board starts off the same way as yesterday. Like I'm going to explain to you today what it was that was on the board yesterday that is ultimately the purpose of this whole train of thought experiment. Um, couple logistical things. Um, um, just as a forward, like you have somewhat of a break. Like I know that now there's a lot of material I need to go over. You've been asked to think about a lot of material on your own, and now it's my turn to start talking about it. You're still being asked to go ahead of me in the material. That's always the way it works. Physics does get challenging that way. But stay with me. Note that so I still have to go over this, like homework 3, and then there's definitely homework 4 to go over, which of course is challenging. And I know that. And I will get back to that next. So you don't have any new homework due Monday. What I'm trying to say right now is you don't have any new work Monday. So you have time to start catching up. And the more thing, even though nothing I say today will directly seem to help you with homework 4, I recognize that, but still it'll give you more time to think and discuss with other people and try to make your way through homework 4. And then or revise it or do or complete it even if you didn't for today, etc. But then but there's nothing new due Monday. Then Wednesday, just to be clear, I'll put this in Google Classroom later, but I won't be here Wednesday. Wednesday, we will not have synchronized class. That will happen from time to time in this course. So that's the reason, if you notice that there's a video that you're supposed to watch for Wednesday, and there's like the regular homework for Wednesday, but you'll notice that the homework is not due till midnight rather than at the beginning of class time. And the video you're just supposed to watch, it doesn't like have any point values associated with it or anything. There's nothing you're supposed to submit. Just watch the video because it'll help you with the homework, I hope. And also the reason I'm asking you to watch that video is it's kind of to substitute for the class time that we won't be together. So it's like asynchronous, technically this is a blended or whatever, blended modality or whatever. So technically Wednesday won't be synchronized. Instead of class time, you'll watch that video. And then and then you have till midnight to do the homework. Of course, you can all help each other, blah, blah, blah. Of course, I know that you won't get it all perfectly right. You're trying your first draft. Then I'm going to come in and start explaining things more. Hopefully the video will help. Of course, you can always play all the old videos for help as well. But lastly, just so I'm just warning you, you don't have to, you won't come to class on Wednesday of next week, and there will be a posting like the night before in Google Classroom, and it'll even give you points for even responding. Like once I explicitly tell you you're not coming to class Wednesday, please respond to this by saying yes, you'll get points even just for doing that. And then I might also say something like, I want you to answer these couple of questions about the video that I posted. And then, that's like your work for the class day. So if you get a thing like that, if you get a portal like that, there's points associated with it, even just for saying yes, just so I know that that it's clear that you're not supposed, I don't want to waste your time and have you accidentally come to class today. So that's the way I always do. So just look out for that next week, that there'll be a portal that will say, as long as you understand you're not coming to class next week, tomorrow, Wednesday, the 25th. Yeah, Wednesday, the 25th, then just, or you get my point. But it'll all, anyway, that's just a warning if you're trying to plan your calendar. Okay. So again, stop me at any time if there's questions. But what I want to go to now is to start explaining like what the heck this is on the board and what it has to do with this crazy train thing that you did yesterday. Okay. Just changing the view on the screen. Okay. Actually, I'm sorry. The train. Okay. And please I have a PDF. I'm going to turn the page soon. There's plenty I wrote down for you, but I'm going to go on a rant. I'm going to warn you right now. I'm going to talk for a bit before it even refers to direct notes. I'm going to talk for a bit, and I would really encourage and ask you to take notes on what I'm about to say and even submit them for points. Like I'm about to say some stuff that's not written down because I don't want to mess with what's already written down. But it is information. I suggest and strongly request that you write it down. Okay. The piece of information number one is that what you did yesterday or what you did at home with the train of thought exercise, it was hypothetical, but that doesn't mean it was fiction, and it doesn't mean it was meaningless. What you did, strictly speaking, was called a thought experiment. In fact, in physics, what that's really called, it's called a Gedanken experiment. Gedanken. Gedanken experiment. Gedanken is it is German for like thought. So thought experiments are a big deal in physics. A lot of Einstein's groundbreaking work was presented in the form of thought experiments. A lot of Galileo, not all, and a lot of Galileo's groundbreaking work was presented in the form of a thought experiment. A thought experiment is a real thing. It's a real thing in physics. It doesn't mean just making up whatever we want to make up. It means setting up a scenario in our mind and then running the film in our mind. Instead of running the film in reality, running the film in our mind. And the assumption behind a thought experiment is if we watch what would happen in our mind, often many of us, once we set up the mental film under certain conditions and properly, our minds are all similar enough that if a thought experiment is designed sufficiently well, we can have confidence that many of us will end up seeing the same end to that same film, that we'll all come to the conclusion of how the film would play out in our minds once we set it up, because our minds work similarly and our minds are considering what would happen in nature, and nature works one way. So in other words, sometimes it's like an argument. It's like, look, if you consider this and this, wouldn't you agree that this, and this would happen? And if you would agree with that, doesn't that tell us something about nature if we all already know that, right? In other words, like, well, I think you get my point. It's a valid way of figuring something out in physics that then eventually has to tie back to real experiments. Either it has to be motivated by data that we actually collect in the lab or lead back to the new collection of data, like a new design for how to collect data in the lab. But there are things that our minds can agree on would happen in nature, as long as we agree on the ground rules of what we're setting up in our mind. All right, so anyway, the train of thought is part of an actual tradition in physics known as Gedanken experiments. Galileo was fond of it. Einstein was fond of it, just to name two. So what was the point of this? So that's like one thing you could write down. Okay, so the next thing is, what was the point of this train of thought experiment? So maybe this is item 2 if you're taking notes. What was the point? Well, let me start by saying, if I'm going to defend it as a thought experiment, if I'm saying that it actually has validity in physics to show us something, I'm going to pause for a minute and say, raise your electronic hand if any of you, if at any time, in any moment in your life, you, even for a brief moment or a minute, if you ever experienced any kind of the confusion that we're laying out in train of thought, like, has there ever been a circumstance in your life where for a couple of minutes you actually weren't sure if you were the thing, if you were moving or something was moving past you? Like if you've ever been in an elevator or an airplane, or you've ever been fooled. Have you ever been confused or mistaken, even for a moment, about whether you were moving or not? So my question is, can you raise your electronic hand if you could relate? Thank you. All right, awesome. Howard, thank you, Emanuela. Thank you, Yaneli. Thank you, Gabriella. Thank you, Sanam. Thank you, Ariana. Thank you, Sydney. Thank you, Genesis. Thank you, Roger. Thank you, Brian. Awesome. Right. Okay. So hopefully, and I'm keep them up for a second. Keep them up just because I want to see if the other people see. Like basically, what I'm asking is, yeah, keep them up if you. Thank you. Because basically, what I'm asking is, even if you thought train of thought was silly or stressful or a waste of your time, what I'm really asking is, that may all be. It may have felt silly or may have felt like a waste of your time. But did you think it was relatable? That was not a word when I was growing up, but it's a word now, and I love it. Did you find it relatable on any level at all? And the people that have their hands up right now are saying, yeah, it was relatable. Like, again, they're not saying it was brilliant. They're not saying that we like, like they want to think about it all the time. But like, and if those of you who don't have your, I mean, okay, so some people in the room are saying it's relatable. You could put your hands down. Thank you. I'm wondering, the people that don't have their hands up, actually, wait, yeah, put your hands down. Yeah, I'm gonna do, here's another thought experiment. Just to be a jerk, I'm gonna do the control right now of the experiment that I just ran. Just as a control, I want you, and you can put your hands, well, all right, here comes the control. And Andre, you can put your hand down now. I totally see it, so thank you very much. Well, here's the control of the experiment. Everybody, raise your hand if you are hearing me right now. Like, raise your hand if you're in the class paying attention at all, and keep them up. Just keep them up. I know it's like the cruelest thing I do, but just keep them up. If you hear me at all, even if you don't understand me, if you hear me, if you are present, raise your hand. Okay. That's totally awesome. I'm not trying to shame two people in any way or call attention to. Okay, awesome. Thank you. Awesome. So, wow, 100%. Okay. Phew. Look, I don't really want it. All right. So you're all here. So now, I want to see this again. Now that all of you are here paying attention, take your hand down if you found train of thought relatable in any way. Like, I just want to see if I'm grabbing everybody here or not. Like, if in any time in your life you experienced anything, even for a minute, even if you were on drugs at the time, or like whatever, or like whatever, or sick, like, did you ever get confused? So take your hand down if you can relate at all to any aspect of what happened in train of thought. Like, okay, so some people really cannot relate. That's fine. That's on, or well, okay, I'm gonna do, oh, okay. Or just, okay. I don't know what, okay. Again, I'm not trying to, okay. I see you. Do you see me? Where am I going with this? The first thing I'm trying to say is so point 1, train of thought was a Gedanken experiment. It's a thought experiment. Point 2, I think it's a relatable one. I think many of you do too. Like, I think if you, I'm going to change the view on the screen now. I think, honestly, if you've ever been on an airplane, if you've ever literally been on an airplane, even if you don't think you were confused, even if you think the whole time on the airplane you knew you were moving, like, come on. If you were on an airplane and it was especially long enough trip, if ever the airplane like achieved cruising speed, and the pilot said it's now safe for you to unfasten your seatbelts and walk freely about the cabin, if any time you're on an airplane, you ever did unfasten your seatbelt actually at all, but let alone get up and walk to the bathroom, like, you might think intellectually that you understood that the plane was moving at like 500 miles an hour or 600 miles an hour. You might think that you thought that, but if you open your seatbelt and got up and walked to the bathroom, and among other things, were not afraid that the back of the plane was going to slam you in the butt while you were walking, right? Or if you even like stepped up, maybe if you even jumped because you were so excited that you were getting to Tokyo soon or whatever, if you jumped up and you assumed that you were going to land in the same spot when you jumped down, right? Or if somebody said, could you pass the peanuts? And you just passed it to them and you didn't go, all right, here you go. Here come the peanuts. Like if you were just like acting like, or and let alone if you complained that the movie was bad or that the food was bad or that the person sitting next to you was like ugly or that's weird or whatever, you were treating the airplane the way they want you to treat it, which is like your own freaking hotel room, right? It might be a very uncomfortable hotel room, but like if you get all cozy and like walk into the bathroom and whatnot, your body is acting like you're in a box rather than a sealed cabin hurtling through space at 500 miles an hour, 5,000 feet above sea level, right? Like you are kidding yourself. Like you are, if not confused, you are certainly experiencing cognitive dissonance if you act natural in an airplane. In fact, if you get in an elevator, once the elevator takes off, like once the elevator is starting to move, it's like one thing, your stomach is a little bit like, and then once it's like coming in for a landing, it's, but in between, if you're ever in an elevator and you're chatting with your friend, like, oh my God, that exam was so hard or whatever, I hate that like you're forgetting, like your brain is allowing you to totally forget that the thing is moving, right? We all the time are in some sort of confusion about whether, or it may not be concern. You might not care. You might not be wondering all the time, and neither am I all the time. But somehow there are times when we seem totally to be in motion and yet we don't seem to be at all, and vice versa. Vice versa. What do I even mean by that? And there are times. Oh yeah, and well, and vice versa. I won't get into the details of vice versa, but like, so motion is a very confusing kind of thing. Like we're gonna get back to all the math and all of that soon, but I know this is like confusing to stick this like interlude right in the middle of when we're starting to build the math. We're gonna get back to the math. Believe me, we're gonna have equations coming out our ears for the rest of the semester and next semester. But if you're noticing something in the 5-step method, hopefully you're noticing that my theme is what's hard. Or if you notice, if you started homework 4 and you handed in for today, great. You might have noticed it's starting to require a little bit of thought. It's starting to look a little mathy. You're starting to have to do things that I haven't explained. And if you're like me or like other people in homework 4, you might be starting to experience that thing of, I bet I could do the math. Like the math doesn't seem that, I mean, it's like algebra. I bet I could do it. But I don't know how to start these problems. Like more and more, if you ever have the experience in physics, I think I know what to do if he shows me or if he gives me a push forward, but I really just don't know how to begin. Like I just don't know how to set it up. Right. If you've ever experienced that in physics, that's going to happen more and more. I'm here to say, yes, welcome to physics. The hard part of physics is not actually the math, even though everybody thinks it is. You're equipped with the math. It turns out in physics, a lot of people end up using the math as a crutch to do physics. Once it's a time for computations, if you've gotten this far in your scientific life, you know how to do computations to a certain level. And that won't be the hard part. The hard part is how do you set up the computations? What are the computations that we have to do? And what I'm here to tell you is how to know how to set up the math in going forward, whether it's homework 4 or homework 5 or whatever. More and more how to set up the math comes down to steps 1, 2, and 3, particularly 3. And 3 is when you're supposed to write down general definitions or principles that are true even before you start the problem. Well, today I want to give you one of the biggest principles of all, the law of the laws that tends to be what physicists are thinking when they know how to set up a problem. Like this is the secret to the kingdom. Really, I don't mean to be cheesy, but what I'm doing today, and why we're doing a conceptual interlude today, is because I'm trying to give you the fundamental concept that actually is what's behind how physicists set up and solve problems of any kind, classical or modern, 203 or 204 or whatever. There is a principle underlying the laws of physics that we always have in our mind when we're trying to figure out how to set things up. And the principle comes from train of thought. So wait, okay, I'm getting myself again. So point number one, if you were taking notes, point number one is train of thought is a Gedanken experiment. It's a thought experiment. Point number two is, I think that we can all agree at some level it's relatable. It's not fiction. It's hypothetical. It's a composite of experiences that we've all had on Earth. And I think if you live on planet Earth, and especially if you live in modern technology, you've had an experience like train of thought. That's point number two. Point number three is the experience. So I'm saying point number three right now. If you've had the experience ever of train of thought, then you are like generations and generations throughout history that led us to the point of beginning a field called physics. If you've had the experience at all, you are like the people that ultimately started us off with a scientific method and principles for solving physics problems, specifically Galileo. I'm saying in point number three that the takeaway from train of thought you're going to see is the fundamental principle of physics, the fundamental step three that's always in the background and always true. When in doubt, if you can't think of anything else to put as a step three GDP for a homework, consider what I'm about to explain to you. Okay, that's what I'm saying in step three. This is going to be the granddaddy of all GDP step threes for solving problems. That's like the link to the rest of the material. Point number four in the notes that I'm giving you right now, point number four is that train of thought gives us the grand principle of physics because of ultimately of something that a couple of you said yesterday. A couple of you in the room observed, I think it was more, it was at least, I think it was at least two people in one way or another. I mean, you all did great. You'll see everything you were thinking was totally valid, and everything you were thinking and saying was like, was not only valid, it's part of a dialogue that's been going on for centuries in physics. But in particular, a couple of you said, well, wait a second. Like when you're asking, are you moving, Yaverbaum, when you're saying, are you moving? Like a couple of you said, well, I mean, even if the train is moving, I might still be sitting still in the train. So I'm not even sure exactly what you're asking by the question. Like I'm not moving in the train. I'm not moving compared to the train, but the train might be moving. So first of all, I don't even, like when you say, are you moving? Do you mean like me or the train? Or do you mean me compared to the train? Or do you mean the train compared to the platform, right? Very valid question. Super valid question. And then someone else said, well, wait, for that matter, actually, I mean, don't we always know that no matter what the train is doing? Now, here's the key right here. Point number four is about to come. Someone said, honestly, Gabriel said, wait, isn't the train like on an Earth? And don't we already know, even going into this thought experiment, don't we always already know that the Earth, oh wait, Gabriel's in the other, sorry, anyway, don't we always know that the Earth is always moving? Like, don't we know that? Like, isn't the Earth like always moving? So like, actually, no matter what we're saying, I mean, when you say Yaverbaum, are you moving? Is the train moving? Like, if you're asking like, is the train moving at all? I think so, at least one person said, it seems to me, even if the train is like parked at the station, the station is attached to an Earth and the Earth is moving. So like, no matter what, isn't the train moving? Very fair point. Not a technicality. Not a technicality. What I'm saying in point number four is, if we start considering this train of thought in light of the Earth, then we really start thinking physics. Point number four is, let's consider the Earth. Point number four, in effect, is like, wait, if the Earth is already moving, doesn't that just mean automatically that the train is moving? And by the way, that doesn't mean that any of your other thoughts were stupid or a waste of time, not at all. But it is interesting and important to note that there's this thing called Earth under the train. And yes, we've all been told since we were in third grade that the Earth is moving. So let's go to point number five now. Point number five is, we've always been told the Earth is moving. Why do we believe that? Like, let's pause for a second. I know we've been told it. I know we've been told that the Earth has always been, we've been told it. I was told it. You were told. I'm not saying you shouldn't believe it, but I am saying let's stop and consider for a minute the earth is moving, i.e. the ground beneath my feet is not actually stable. That's if like me, so again, we're on 0.5 here, the earth, and that's the only point. I'm going to go on a little rant right now. I'm warning you. I'm going to get a little overexcited, and any of you who has me for any other class or has had me before will hear the same. Like, sorry, I'm about to do that rant. It'll take a little while, this rant that I'm about to do, but it will segue us into the rest of the PDF that's on the board here. So you're done with notes that are off page. Point number 5 is the earth. Let's go. Let me now talk to you about the earth for a minute. And I'll show you how it links us to Galileo's principle of relativity, which is the board notes. The earth. Okay. When I was in 3rd grade, I too made a solar system model out of like grapefruits and watermelons and ping pong balls or whatever. Like, I don't think there were ping pong balls involved, but like there were fruits. And to this day, my father, who is still alive and well and very smart, to this day, he remembers sitting down, like we talk about it to this day, when he sat down with me with like fruits and we like did the thing. Here's the sun, here's the earth. And like it was a pivotal moment. And I was learning from him what I was supposed to be learning for 3rd grade, which is that the sun sits over here and the earth goes past it like all the time. And just like these fruits. Okay, so I learned what I was supposed to learn. Very nice. When I was learning that, I was even learning it in the context of a science class where they made a big point. And I remember that. And maybe I'm compositing different memories together, but somewhere in my youth, I was taught something along the following lines. I think you can relate. I hope you can relate. Like that until Galileo's time, until like the late 16th, early 17th century, people tended to believe or act as though the earth was sitting still at the center of a universe. That earth was sitting still, and that the stars and the sun and the moon and the planets all went past the earth every day, like in these big cyclical motions every day from east to west, that the earth sat still and everything moved past it, that people believed that for centuries and centuries and did stuff with that understanding for centuries and centuries. And that these people that believed that included like the church, which had a lot of power and a lot of information, stuff like that. And that, according to the story, I'm saying, and according to this story, this narrative that I learned, Galileo was so advanced and so courageous that that even though everybody around him and everybody with authority was saying the earth sits still, the earth sits still, Galileo apparently had the courage to say, no, wait a second, just because people are telling me, just because powerful people are telling me to believe a certain thing, that's not good enough for me. I am going to I believe in the evidence of my senses, and I believe in the analytical faculty of my mind. And I believe that if I start developing a method where I can literally collect data through my senses from the outside world and start developing a controlled, reproducible method for designing experiments that will allow me to gather data from the outside world and put it into my brain and then churn it through a linguistic crank, that if I develop a method for doing experiments, for collecting data, for then analyzing that data, then that method I could do over and over again and really start getting data that I can really trust over time. And I could pass that method to other people. And so that even if I'm just spinning my own wheels or coming to conclusions that are misguided, even based on this sort of good data, then they have the instruction manual for collecting their own data, and they can check on my data and check on their own data and check on my, and if I hand out this instruction manual, if we all start doing this, start actually reproducibly and repeatedly collecting data from the empirical world and writing it down and like measuring the response of one variable to another at a time and passing this all around, then soon we'll have not just me spinning my own wheels or just you spinning your own mental wheels, which may be very, very advanced, but we'll have us all tethered to an actual like sandbox of information that is available to all of us. and that we're all analyzing according to the same rules. So we'll get closer and closer to actual truths that have to do with the actual outside world in which that sandbox is located. And it won't just be a bunch of individuals spinning their own mental wheels. It will be a scientific method that will allow us to have more confidence in whatever we're deciding up here, because it'll all be tethered to what's down there in the natural world that we're studying. Now, people have been studying the natural world for thousands of years, but they tended to look at it and then say things, which is super advanced on its own. But he's saying, no, let's actually systematize the method for looking at it and control the method so that we're all looking at it the same way and getting the same data and then going into our minds. So it's not just individual minds, it is a collective of, etc. This is called the scientific method. You've heard of this a million times, right? Okay. Sorry, I'm getting so excited about it. I totally forgot that. So I love the scientific method. And I was taught in third grade that Galileo was the hero that came up with the scientific method and basically said, don't just trust because somebody or somebodies say something, like actually collect the data and run the experiment and trust your senses and like relate your senses to other senses and da-da-da-da-da. So Galileo was a hero for saying, I don't accept dogma blindly. I do stuff and I use my senses and trust the results, right? Fine, great, sounds great. Sounds almost like I'm excited for science as a third grader. Let's go, let's do it. But then after all that, and again, I got overexcited and sort of got in the weeds of that. But the point is that I was told somewhere or another that Galileo was a hero for developing a scientific method that had to do with senses and thought rather than just accepting authority, right? And so the conclusion of all of this narrative or of Galileo's work supposedly is that then Galileo comes to the conclusion that even though you're all saying the earth sits still, I'm going to say the earth totally moves all the time around its own axis and past the sun. Now, again, he's not the first person to have come up with that. He's not the first person to have come up with that. But he is the first person to go out on the limb that he went out with it and to get that public with it and to get in that much trouble for it. I was taught that he was like a hero for doing this, for going against blind dogma and actually trusting senses and thoughts and having the guts to say the earth moves. But then I was taught in third grade, therefore, the earth moves. Go get your watermelon, go get your cantaloupe, make the model. Now you know the earth moves, and you know Galileo is a scientific hero. Let's now go do science. And for me, and I don't think I'm the only one, I was like, wait, hold on. I mean, I wasn't consciously, but something happened in that moment to me that turned me off to science. It is one of the greatest science stories ever, but it turned me off. I mean, I'm a physics professor, right? I hated science for years, not literally just because of that story, but because that story is one of many, many examples growing that as a child, science was presented to me in a totally confusing way. So confusing, I didn't even know I was confused at the time. I was getting two messages at once. One, science is about going again, not just accepting authority blindly, but rather accepting the evidence of our senses and the evidence of our analytical faculties. So that's one message. Don't just accept things because you're told them by authority figures, like do stuff. And that's the amazingness of science. Great. Sign me up. But then the other message is, so therefore the earth is moving all the time underneath your feet, all the time. You're standing on a rock that is hurtling through space all the time. And why should you believe it? Because Galileo said so, and I'm your third grade teacher, and I'm saying so. Like, no, but why? Wait a sec. Hold on. Why should I believe the earth is moving? Because Galileo found out that there's, yeah, but you're just saying that, right? Yeah, I'm saying Galileo, and he's a hero. He was a scientist. So he found, yeah, but hold on. I'm standing on the earth. It doesn't seem to be moving at all. There's no evidence, like where evidence of my senses. I thought science was evidence of my senses. I'm standing on the earth. I feel fine. I'm not throwing up. I'm standing. And if I jump on the earth, I don't expect the wall of my house to come slamming into me from the west. Like, right? And I don't think birds have a harder time flying west than east or the other way around, right? What do you mean the earth is moving all the time? Like evidence of my senses and logic. If the earth were moving all the time, if I dropped a baseball, wouldn't it land like behind me rather than on the floor? What do you mean? Like science, you're telling me the earth, and they're like, well, they weren't literally like, they're not bad people, but they're like, no, Galileo said so. Like, Galileo's a great scientist. Like, no, look, soldiers go around the sun, cantaloupe. And so I did what many of us, maybe for one beat, I might have even thought something logical, like some of you might think. I might have even thought something like, okay, okay. I mean, I guess I'm missing something. Like, they seem so sure, and like they don't seem to be seeing my like, okay, I guess the Earth just moves. So then for 1 minute, I was like, I guess the Earth moves so slowly that I don't feel it. Is that your point? Like, it's like moving, but it's like, is that like the deal? Like, and in fact, I think many of us think that it's totally logical to think like. So I thought, okay, is that the point that you're telling me it's moving, but like so slowly that it doesn't even like really, well, that would be reasonable, except for one fact, which is that it's totally not the case. And it's not what Galileo was claiming. Like, just for the record, just FYI, if you believe that the Earth is moving, if you believe which I'm not saying don't, but I'm saying like, let's consider it for a minute, what it is that you're believing. If you believe the modern heliocentric model of the solar system and of the universe and everything, to believe that the Earth is moving, according to this model, the Earth is spinning around its own axis, from west to east. It's spinning around its own axis at like, say, if you stand at the equator, like near upwards of almost 1,000 miles an hour. And if you're like in New York, like let's say 650 miles per hour, like that's just spinning around the equator. That's near the speed of sound. Just the Earth spinning, like close to, like, let me say that again, like I'm rounding, like 700 miles per hour. That's faster than most airplanes. That supposedly the floor is just going around the axis all the time, faster than most airplanes. But then while supposedly we're going past the sun all the time, hurtling through space, attached to nothing. And you know what speed that is? That ain't slow. And you could look it up. Like right now, you could Google it. I'm not making this up. It's like 65,000 miles per hour on average. 65,000, supposedly, just to be clear. Those of you who said, well, aren't we on an Earth that's always moving? You're not wrong. Like, you did your homework when you were in third grade. You are a good citizen. You are correct. But what you're saying, if you accept this idea that we're on an Earth that's moving all the time, you're believing that we're moving all the time at 65,000 miles an hour. Let me be clear. For a rocket to achieve escape velocity and leave the Earth's orbit, the Earth's atmosphere, and go to the moon, which wasn't even possible until 1969, for a rocket to do that, it has to go 45,000 miles an hour. We're saying that we're standing already on a surface that's already going 20,000 miles an hour faster than that. That we're moving all the time through space faster than a rocket has to go to the. What? What? Am I saying this is wrong? No. But I am saying, number one, consider either it's crazy or it's right for reasons that are crazy or so interesting that they must be worth studying. When I heard the Earth was moving in third grade and I was not given an explanation for that, that was the beginning for me of a long period of just assuming science was just another way of talking about, like, obviously whatever they must mean by motion or Earth is something different, because my Earth is not moving. So in my normal brain, I was like, Earth still. And then when I went to science class, I was like, okay, the Earth is moving at 65,000 miles, and I just like would do stuff like many of you. Not because you've chosen to do science, so good, but like I, for a long time, just thought science was like whatever those people are talking about. I can do it when they ask me to do it, but they're not talking about my universe, and they're not using words the same way. I'm here to say, no, they are trying to use words the same way. They're saying something very powerful when they say that the Earth is moving, and they're saying something potentially correct if you get your mind around it. But just saying that Galileo said it is not good enough. We need to understand what it was that Galileo was thinking. And by the way, how did he convince? If he got almost burned at the stake for this, and instead house arrest, if people were this upset over this idea, it was not because they're crazy religious freaks, not at all. Like, they were religious, but that's not in itself freakish at all. Like, they were being as logical as you or I when we say, I look at the ground, it ain't moving. I look at the sky and it's going past me every day. The stars at night are going past me east to west. The sun during the day is going past me east to west. Like, all of my senses tell me that stuff is moving past me. Galileo, if you're going to tell me that the Earth is actually moving past the sky, I need a reason to believe that. Like, why should I totally, like, why on Earth, no pun intended, should I believe you, Galileo? When they were questioning that, they had darn good reason to question. And then they go a little bit further. I'm almost done with my rant. Like, and they were just like being like, they were like, what? Fine, you're inventing science. Very nice. You're inventing science. Like, first of all, you're inventing it. So we don't even know what you're talking about. There's no reason we should use that as I mean, that's like Yaverbam just walking into a room and saying, I am now inventing a new form of school where you all have to get Fs and I have to get a raise of $100,000. And the new form is called Yaverbamism. So I've invented it. So now you all like, what? I mean, you can't just like invent something and expect, you understand what I'm saying? So they're all saying, Galileo, what? The Earth is moving? Like that bears no relation to any kind of sensory evidence or logic. So you got to tell us some reason to believe this, that the Earth is moving at 65,000 miles an hour. Okay. And so I'm going to tell you, wait, am I forgetting? But he does, and it's worth knowing what he says. And in fact, what he says in various different ways and in different books, the argument he makes for why we could possibly believe that the Earth is moving, not only ends up being consistent with physics, but this is what physics is based on. Like literally, when we say that Galileo is the founder of the classical scientific method and the founder of classical physics, we actually mean that the way he resolved this Earth motion question, the arguments and the data that he brought to bear on the question of whether the Earth is moving or not is actually what formed the foundation of everything that we now call physics. Like literally, like I'm about to show you that even the laws that we have in physics, laws of gravity or Newton's laws of motion, which we'll do next, all those laws and everything start from a principle that Galileo established in trying to argue for the Earth's motion. The principle that he established in trying to argue for the possibility of Earth's motion, that principle, maybe this is point 6 that you should write down. Galileo's principle is, it's like an analogy, like a Miller's analogy, like the colon, bleh, colon, bleh, colon, bleh. You know what I'm talking? Like something is to something, as something else is to something else. Like Galileo's principle is to physics laws as the United States Constitution is to state laws. Like literally, I'll say it again, like the principle is to laws in physics as the Constitution is to laws in our country. This is the law of laws. This principle that I'm about to show you right now, which just comes from debating over the Earth, this principle is where all the other laws flow from. And this principle is so foundational that it itself comes in a series of different forms. Each different form of this principle from here on in is a topic in this class. Every topic we do in this class relates back to one of the forms of this principle I'm about to tell you. And so whenever you're in doubt in any homework, as it's getting harder and harder, whenever you're in doubt at step 3, GDP, like what am I supposed to write down that's like driving this problem? If you're in doubt, turn your mind back to the various forms of this principle that I'm about to give you. Remember, GDP stands for general definitions or principles. Here's what I mean by a principle. There's one that drives this whole class, but it comes in different forms. Like there's different ways of saying it. That's what I'm about to explain right now. Last beat before I forget. So again, if you're taking notes like off margin, like point number 6 is that Galileo's, I just said it. Yeah, Galileo's principle is to physics laws as the United States Constitution is to United States or state laws. Now, one last item before I start turning the page and talking about this. It seems like I just went off on a crazy rant again. I mean, I did because I care about, this is what, to this day, no matter what physics I'm doing, this principle gets me more excited than any other aspect of physics. I never get bored of it. It is the driving engine behind physics, this principle that I'm about to explain. But if you didn't already see the connection, the actual connection here is that train of thought. When you're sitting there going, is the train moving or not? What you're really doing is putting yourself in the mindset of people all throughout thousands and thousands of years of astronomical and scientific history. Like for the thousands of years that people stood on the rock that we call Earth, when they stood on the ground and either assumed that the ground was stationary or started wondering, could it be possible? Like that, all that, like when they started wondering, all that stuff is moving past us all the time. It's a lot of stuff to be moving past us all the time. It's a very complicated set of patterns that that are involved in all of these stars and this sun and moon and all of these planets moving past us all the time. When people started wondering, wait, are they moving past us, or is it possible that I'm moving past them? That's what you're doing in train of thought. To ask whether the train is moving or not is really to ask yourself what anything and everything that people ask themselves when they try to figure out whether the earth is moving or not. And when you say, I think I need more information, that's what everybody says through history. I mean, everybody who's thinking about it. And so then when the white lights come into the train, those white lights represent stars. And I think most of you found, or I found for most of you yesterday, no matter what you were saying about the train at the beginning, many of you you're like asking for more information, and many of you got more information once you saw that the white lights were moving. You got more information, and a lot of you even changed your answers. But it still didn't definitively resolve the whole thing. Just like in the history of civilization, we see all these white lights moving past us every single night, and they all move in a formation. Just like those white dots in train of thought, they all move in a formation together, which is already either simplifying or mystifying. Like, how could a 1,500 dots of light all move together, all like every single night? Like, that would be a strange coincidence that all of them are moving together all the time. Maybe could it be more easily to believe that we are moving past them? Like, I got a lot. And then it turns, so we look, so it doesn't resolve. It just enhances the question that there's these white lights moving past us. Now, it turns out in history, it turns out if you look closer, there are a couple of lights within that formation of lights that are doing different things. Like there's a sun that's also moving east to west, but a little bit slower than all of those other dots. And then there's this big white disk called the moon that's also moving east to west, but slower than the sun and slower than all the rest. And then there's these 5 other dots that look like all the rest, look exactly like all the rest, like you would never call them anything but a star until you start really paying attention to these stars that are moving all together. And it turns out there's 5 others that are actually moving differently from all the rest and from one another. And those 5 are Mercury, Venus, Mars, Jupiter, and Saturn. They're only Jupiter and Saturn, or we call them Mercury, Venus, Mars. They don't look any different from the others. We don't know what they're made of, like for most of history. We call them planets because planet is the Greek word for wanderer. And all we know about these other 5 dots, plus the sun and plus the moon, for most of history, including right up through Galileo, all we know about these 5 other dots that look indistinguishable from the other 1,500 that we see every night with the naked eye is that they don't stay in formation for all the others. So this leads to a lot of tension throughout history. Like, wait, there's 1,500 that all move together. That's, I'm approximating. It's like anywhere between 1,000 and 2,000 that you could see with the naked eye on any given night. I mean, if you don't live in New York City. So there's like 1,500 that are all moving together. That's already like, what? Then there's like 2 that are bizarrely large and bright that are not moving with all the rest. Okay, they're bizarre. I guess they're special. But then there's 5 that don't even look special at all, that you wouldn't even notice at first, except if you're paying enough attention, which you totally can do for 2,000 years, even with your naked eye. You start noticing that those 5 that you call Mercury, Venus, Mars, Jupiter, they don't stick with the canopy of all the rest. They're somehow special. So they wander across the canopy. So you call them wanderers, planets. And then you start saying, wait, there's 1,500 that go all, but then there's 2 that are, and then there's 5 that look the same. Like, what? This is so complicated. Like, how could all of this be happening and why past us sitting at the center? And it starts getting more and more tense. So there's real question as to whether we're moving or not. Just like there's a legitimate question of you on the train. Am I moving or not? And we need more information and more information to solve it. So finally, Galileo has a telescope. He doesn't invent it, but he has one, and he's one of the earliest people to have one. And he's certainly one of the first people to take his telescope, and instead of pointing it across party rooms, and forgive what I'm about to say, but this is historically, instead of using his telescope the way the person who invented it used it, which was as a parlor party trick, the person who invented it would use it to look across the room, since no one had one besides him, he could look across the room at a big fancy party and look at women across the room without them knowing that he was looking at them. Like, and then he would show other guys and other smart guys, like, look at this, ha, ha, ha. And I'm not trying to be offensive. Like, it is offensive. That's what it was first. And the Galileo's like, that's really fun and everything. Like, that's cool. And, I like to party too. But actually, I feel like we could do more with this device than just that. And he went home and built his own, which is amazing in itself. He quickly ground lenses, put them together, and made his own telescope like super fast. So he didn't invent it, but he adopted it super. This is kind of like a Steve Jobs or Bill Gates kind of story. He adopted it really fast for like grander purpose, and then started pointing it to the sky and looking at things in the sky and sketching what he saw night after night, regularly, making very careful sketches of how the sky changed from night to night through a device that brought him like 4 to 10 times closer to the stars. Now that's phenomenal. And there might have been another person or two people doing that, but he did it faster and more, like in a more organized fashion than anybody else who was doing that. But again, the telescope just got invented. Barely anybody had one. Now he's made one really fast and really well, and he's using it to make sketches and to stare at the sky like before anybody else, and does it so regularly and so quickly that he quickly publishes books. Like, he's in a race. He publishes books of his sketches and of his thoughts about what he sees. And based on this fact that he's now 4 to 10 times closer to the sky than any human being has ever been before. I mean, like, literally, right? Like he knows, literally. He's just, in effect, traveled in space to get a closer glimpse of the heavens than anybody in civilization, because no one's had a telescope before. And that's just true. He starts getting more data that strongly suggest, it makes it harder and harder to believe that the Earth is sitting still. I cannot get into the details of all this right now. I have books on it that I can lend you or read to you later and stuff like that, or I could talk to you about, but I can't get into all the deep. But basically, he sees things that no one's ever seen before, such as moons of Jupiter. Like, literally, like, they pop into view, because like these 4 dots pop into view. They've never been in view before. Now he can see them. So it's like 4 more dots that no one ever seen. And he's seeing that they're literally going around Jupiter. No one's ever seen that. So he's like, wait, there's like a world going around a world? Like, wait. So, I mean, if Jupiter can be the center of its own little world, I mean, doesn't that strongly suggest that it's possible that we're not the center of the whole world? Like, it doesn't prove anything. But he starts seeing a bunch of things like that strongly start suggesting that it really is possible, and maybe even simpler, to believe that the Earth is moving. And so he starts publishing this idea. And of course, the world goes, what? Like, really? And so the first thing they want to know is, okay, look, even if you're going to tell us that we come over to your house and you shove our face behind the end of this can that you're calling a telescope, and even if you say, look at this black screen at the end of the telescope with these 4 white dots on it, even if you tell us that somehow, because of us sticking our face in this weird, witchy, crafty thing that you're calling a telescope, and we see 4 dots at the end, and we're supposed to believe that somehow we're supposed to believe you that those 4 dots are like moons of Jupiter, just because you're telling us so, because you have this device that you're calling evidence, but we don't have one and we've never used one, and it all seems like black magic to us. Even if we believe that somehow that suggests that somehow the Earth could move, like, hello, why don't we feel it? They say to Galileo, it's the same thing in the train of thought, like, hello, even if you got this weird evidence from the skies that you're calling evidence and saying should make us entertain the proposition that the Earth is moving, we're saying, how about the obvious fact that is available to all of us that the Earth isn't moving, yo? Like, how about that we're standing on a stable ground, and when we jump up, the wall doesn't slam us in the butt? Can you explain that? So Galileo, here we finally go, sorry. So Galileo, in a couple of books, one particularly called The Dialogue Concerning Two Chief World Systems in 1635, he says he runs a thought experiment, a Gedanken experiment, for his readers. And he does it in dialogue form. He like has writes a little play among three people that are arguing about all this. So it's like a soft pitch. It's like, easy to read for that. It's actually in Italian, not in Latin. And it's meant to engender conversations like we're having with the train of thought. And he says in the play, or one of the characters who's arguing in the play says like, well, hang on, let's consider a boat, right? They don't have airplanes back then. They don't have elevators, but they have freaking boats. So one of the characters says, look, hang on. What if you were in a boat and you went and the boat was docked? It was like tied up and sitting there. So you go to the bottom of the boat. So you go to the bottom of the boat and you look around, and maybe you even take measurements if you're that precisely inclined. You look around, maybe it's like the captain's office, and there's like a desk, and there's like a clock on there. There's not a clock. There's like a quill on the desk, and this is actually a real example. And there's like a a bowl with like fish like going around, because they had fish back then. And there's like a bowl of fish going around like happy dappy and the desk is stable on the floor, and you're like, okay, captain's office, very nice, captain's quarters. Okay, so you make a bunch of observations. And you have an experience in the captain's office at the captain's quarters at the bottom of the boat. And then Galileo says, or one of Galileo's character mouthpieces says, okay, now imagine you unhitch the rope of the boat and you let the boat go out to sea, and it achieves like cruising velocity, cruising constant speed, constant direction out at sea. And by the way, of course, it wouldn't even be perfect. Of course, it'd be bumping in the water, waves, but it would be cruising enough that even Galileo knows that his people that he's talking to, his contemporaries, know that once the boat is out at sea and sort of essentially cruising, he does a thought experiment, appeals to their minds. Like if you went down into the dock of this boat, once it was out at sea and once it was going like, 10 miles per hour, 15 miles per hour, whatever, like if you went down into the captain's quarters, wouldn't you observe all the same things? Wouldn't you make all the same observations? If you looked at the fish bowl and watched the fish go around, wouldn't the fish just be going around like normal, like not all crazy? And the desk wouldn't be like falling over. If the boat is going at cruising velocity, then the captain's quarters in every way feels the same. So his point is like, hang on, you've had this experience before. You've been in a boat, and just like you people in a train. You know that as long as the boat is moving at constant speed, you can't tell. So that doesn't prove that the boat is going at constant speed. It doesn't prove that. It doesn't prove that the Earth is, but it says, hang on. If the Earth were moving, the fact that you don't feel it doesn't disprove it. Like, if you're going to argue with me about whether the Earth is moving or not you guys, but you, if you're going to argue with me about whether the Earth is moving or not, don't tell me we don't feel it moving. Don't tell me none of our observations show this moving. That's what would happen if it were moving, right? Because Galileo says, and so here's the principle, here it finally comes with 17 minutes left. Galileo says in the writing, the first way he says it, of course, he doesn't write in English, I'm translating, but he says there's a principle at work here. There's a principle that we all know, we just don't know we know it. And the principle, so here's form 1 of Galileo's principle of relativity. The first form is the laws of physics, whatever they are, whatever they're gonna be, the laws of physics are the same at all constant velocities. They apply, they hold still. They are, whatever the laws are, they don't change from one speed or direction to another, right? And if you're like, well, yeah, sure, but what's that got to do with anything? Hang on for a second. Let's first note, doesn't that seem self-evidently true? Like it's a principle, it's even deeper than a law. Because it's not even a law. It's saying something that's going to be true about the laws. And it's saying something that is very hard to argue. You might not see why you care. You might not see how this matters yet. But let's just stop for a minute and realize why it's a principle. It's a principle because it seems nearly self-evidently true. He's just saying if physics is about motion through space and time, whatever the laws are governing motion through space and time, they can't change from one motion to another. If they did, they wouldn't be laws, right? Laws are laws. Like municipal laws in New York City don't change from one human being to another. Then if they did, they'd be circumstances, not laws, right? Anyway, so Galileo says, whatever the laws are, for example, law of gravity. Now, Galileo knew about as much as, like, Galileo knew what Aristotle knew about at this point. We knew that things fall down rather than go up. We don't know all the math. We don't know like GMM over R squared. I'm not saying, but whatever they knew about gravity, whatever they considered to be a law at that time, one thing they knew is the same thing you know, is that if you drop something, it falls in a straight vertical line and lands directly below where you dropped it from. Consider that a law. Like there might be more details to it, but gravity works that way. You drop something, it falls in a straight vertical line, ends up directly below your hand. Galileo's saying, all right, if that's a law, that's got to be true, whether you're moving at 0 miles an hour or 100 miles an hour. Like, it's a law. It can't change based on circumstances. So whatever, and especially a law about velocity can't change once there's a different velocity. It's the law that's making the velocities. So Galileo says, I don't even care that there's going to be, I'm telling you, physics is about to start now. I don't know what all the laws are going to be. Newton's not born yet. I don't know what the law, Einstein's not born yet. I don't know what the laws are going to be, but if they're going to be physics laws, they've got to be the same from velocity to velocity. Okay, so that's the principle. So what? Well, that's form number one. But now consider form number two. If that's true, if the laws have to be the same, all the velocities, then we could phrase that a different way. It directly logically follows from that if the laws of physics are going to be the same at all velocities, then you cannot make an experiment. You can't do an experiment. You can't even design an experiment to measure the velocity of a single object. Let me say that again. You cannot even design ever an experiment that would measure or determine or find out the velocity of a single object. Am I saying velocity is meaningless? Like, wait, what? You can't even measure the velocity of any object? Like, so what does velocity mean? I'm saying you can't measure the velocity of a solitary object. You cannot do an experiment that tells you whether one thing itself, actually in and of itself, is absolutely like moving through space or not. You cannot do it. Why? Because the laws are always the same in all velocities. In other words, in train of thought, or in an airplane, if you were flying. If you were in an airplane and you woke up in the middle of the night and it was dark and everybody else was asleep, and you looked at it and like it was dark and you were like, oh my God, I don't know if I'm moving or not, if I'm already just stuck in the runway or whatever. And even if then you saw like a cloud going by and you were like, yeah, but I don't know. Wait, okay, I see a cloud going by, but I don't know. Like, am I sitting still and the cloud is moving past me? Or, I mean, something's happening, but am I actually, like me, the plane, is the plane sitting still while stuff is going past it? Or is the plane, or is other stuff sitting still while the plane goes past it? You can't tell at first. So you think, all right, but that's just my confusion. Like, that's just because I just woke up. Train of thought is just a hypothetical. I mean, it's not like a real confusion. Like, obviously I should be able to resolve this. I'm a scientist, yo. So you say, I'm going to do an experiment. I mean, especially because you're a modern person, you're in an airplane, for crying out loud. Like you go to John Jay and you're going to work for the FBI next year. So you're like, I'll solve this crime. I will do an experiment. So you're like, and I don't know a lot about physics, but I know enough to know, like, if I were standing in a parking lot, if I were standing in the runway and I dropped an object, I know enough to know about gravity, it would fall in a vertical line and land directly below my hand. And that's true. I'm not yanking your chain. Like, if I were standing in the runway still and I dropped something, it would land directly below my hand. So you say to yourself, that's what I'll do. I'm going to stand up in this airplane. I mean, the captain, whatever, like the light is off. I'm going to stand in this airplane and I'm going to do an experiment. I'm going to drop my peanuts onto the floor. And since I know if I were standing still, they would hit the floor directly below my hand. If they land directly below my hand, then I must be stationary. I must be standing still. The airplane must be still. You say to yourself. But what Galileo's saying right here is, oh, contraire, mon frère. Oh, no. No matter how smart you are, and now no matter how well like design that experiment, like no matter how much technology you want to throw into that experiment, like, no, that is not going to work. That's not, I mean, it's going to work. It's going to do something, but it's not going to tell you anything, because Galileo's saying, dude, if you were standing still, yes, the peanuts would land directly below your hand. That is true. But the thing is, the laws of physics don't change from one velocity to another. So even if you were in an airplane that was going 600 miles an hour and you dropped the peanuts, they would land directly below your hand. Like, in fact, that's why you're comfortable in the airplane in the first place, because the laws are the same at all velocities. So once you're in an airplane and everything in the airplane's going the same velocity, you act the same way you would on the runway. And if you drop stuff, you don't expect it to fall behind you because the laws are the same. Therefore, if the mere thing that makes you comfortable in an airplane, or the mere thing that allows you to be temporarily confused, is not a temporary confusion. What it really shows is there's literally no resolution to this. You cannot, no matter, even in the future, like Galileo's this confident, it's this much of a principle. He's like, I don't know all the experiments in the world, but I'm just saying it literally logically seems necessitated that you couldn't make an experiment to decide whether the airplane was moving past the ground or the clouds was moving past the airplane. Because no matter what experiment you do, it's going to lead to the same result. And that's why you got into the airplane without fear in the first place. So no experiment ever can figure out how fast or one thing is moving in and of itself, like through space. You could find out that something's moving compared to something else, for sure. You could just look and say, well, the clouds are moving past us, or we're moving past the clouds. You could even track it with measurements in the train. You could say, it seems like every hour the clouds are 300 miles like that way. Fine. So the relative speed between the two, like, so yes, you're going 300 miles per hour faster than the clouds, or the clouds are going 300 miles an hour slower than you. That you can say. But as to which one of you is actually like in the universe, like for real, absolutely through space doing something, that no experiment can resolve. So then Galileo says, guess what? I'm experiment man. While I'm doing all this, I'm saying it's one thing for us to think about things in our mind, but it's another thing for us to think of things that come from reproducibly collected data, right? Called, controlled experiments. So Galileo says, so since I'm starting to tell the world, or at least myself, like, this is what, if you want to believe something, you got to take measurements over and over again the same way, and in a way that someone else could then take over and they would get the same results. Galileo says, if we can't figure out, even though all of physics is going to be about velocity and acceleration, all that, all of physics is about velocity, average velocity, instantaneous velocity, change in velocity called acceleration. It's all going to be about velocity, but we better right now establish velocity is not something that a thing can have, at least not according to experiment. And if physics from here on in is going to distinguish itself from philosophy by actually being based on experiments, then Galileo says form 3 says, says form 3, if it ain't discoverable in an experiment, then it ain't meaningful in physics at all from here on in. In other words, he says, form 3, from now on, velocity is not a property of a single object. Like, no object has velocity. I'm just like literally saying that now in physics. So again, even though, this all seems very weird. We're all going to be about velocity and acceleration from now on in physics. But what actually makes physics different from math, what actually makes physics conceptually so exciting and rich, but also so hard in a way, is that at the root, when we say velocity, which is what it's all about, we mean a relation between two objects from here on in. Velocity is not a descriptor of a single object. Velocity is a relational description. It's a relation between two objects. From here on in, velocity is relative. This is what's meant by relativity, even when it gets to Einstein later on. When we talk about relativity, we mean specifically velocity is relative. You can't talk. If I ever say to you, how fast is the train moving from here on in? The problem is in the question. As many of you pointed out correctly, the train itself is not moving or not moving, or it's not moving at 30 or moving at 100. The train might be moving 30 miles per hour past a platform, or it might be moving 100 miles an hour past a person, or it might be moving 65,001 miles an hour past the sun. What the train's doing depends on what you compare it to. From here on in, velocity literally is never a property of one thing. It's always a relation between two things. That's how we need to think about it in physics. And it comes from It comes like, and that's why it doesn't prove this. Even none of this proves that the Earth is moving. What it proves is that whether or not you say the Earth is moving, you would feel it the same way. It proves it's possible and meaningful to talk about it as moving. And in fact, what this is showing is that actually, if we really want to talk about the Earth from now on, we have to talk about it in comparison. The reality is that you don't feel the Earth moving or anything because compared to you, the Earth is not moving. The Earth is still compared to you. And you, or I mean, when you're standing, and you are still compared to the Earth. But the Earth is moving at 65,000 miles an hour compared to the sun. And or you can say the sun is moving at 65,000 miles an hour compared to Earth. It's always a comparison. It's always meaningless just to talk about one object, literally meaningless. If there's only one object in the whole universe, it doesn't have velocity. I mean, right? It's always, and I know, by the way, many of you may have been thinking this for much of your life. For many of you, you may have sort of always, this might be, I'm hoping this is one of those things where for a lot of you, like you always kind of knew this, but you didn't know that you knew it, or you knew it, but you didn't know it was real science. You just thought it was like the way you thought about stuff. I'm telling you, it is real science. If you understand what I'm talking about at all, especially if it's relatable, like you kind of always suspected, so you are right and you are not crazy. And the good news is that physics makes a big, all of physics is really what happens when we take this super seriously and start quantifying it with math. Velocity is relative. It's a relation between two objects. It's not a property of one object. And therefore, last page in 4 minutes left. Therefore, what we're really saying from now on, when we set up a physics problem where we're asked a physics question, from now on, up in the margin, it says GPR. This is just also, this is what I've just given you today is Galileo's principle of relativity in 3 different forms. There's going to be more forms. Every chapter we do in this course or every topic starts with a new form of it, like for real. Every next chapter in physics is just a new like logical inference from the last form. It's all just turning the crank on what it really means to believe that the Earth could move at 65,000 miles an hour and not feel it. So today I'm giving you 3 forms. There's more forms to come. But again, I'm just trying to remind you, these are 3 like ascending forms, scaffolded forms of one idea. The idea is Galileo's principle. The central idea is whatever the laws of physics are, they got to be the same at all velocities. If you accept that, then all of this follows. So among other things, the following: in order to measure or specify velocity, we must always first, I know that's terrible handwriting, we must always first choose a reference frame or frame of reference or coordinate system. In other words, a basis of comparison. You can't, from now on, if you're going to talk about the velocity of an object, it has to be compared to another object. Whatever object you compare it to is called the reference frame. Sometimes we're doing so much in the same reference frame over and over and over again that we get so used to it that we start to forget to specify it. Like we might be doing a bunch of experiments or problems in the lab, and after a while, we're just always tacitly comparing all of our velocities to the lab. So after a while, we might forget to say compared to the lab or relative to the lab, but that's really a mistake. We shouldn't do that. But even if we do, it's because we're tacitly all used to the idea that our reference frame is the lab. The point is there still has to be a reference frame. If we're doing physics right, we have to explicitly choose a reference frame. What's our basis of comparison when we're doing velocity, measuring velocity? And so every problem that we start, especially at this stage of the game, like kinematics, when in doubt, when you're up to step 3 GDP of a problem, if nothing else, well, let me back up for a minute. When in doubt, when you're at step 1, drawing the diagram, and I keep saying you have to put in labels, and people keep saying like the whole diagram is just like a car going forward. Is that all you want for the diagram? From here on in, part of what I really want in the diagram is for you to label your reference frame or your coordinate system. Like if from your perspective to the right is positive and to the left is negative, that's your perspective. That's your frame of reference. You're comparing the car to, I don't know what, longitude lines or something. So you put that in, and then step 3, you have to say, I'm going to compare the car's velocity to the street velocity or whatever. Whenever you choose a reference frame, you're choosing the basis of comparison for the velocity, and you're tacitly choosing the second object that will be regarded as stationary. So if you say a car is going 100 miles an hour, it means compared to a road, that I tacitly have decided is going 0 miles an hour, even though past the sun it's going 65,000. To choose a reference frame is to assign 0 to a particular object. Now, can you just assign 0 to any object you want? Yes, as long as your chosen object, your reference frame, is not accelerated, as long as it's going at a constant velocity, it's 130. This is my last sentence. As long as it's going at a constant velocity, then it is a legitimate reference frame. So all reference frames, as long as they're unaccelerated, are equally legitimate. So your job in a GDP when you're stuck is to choose a reference frame. Any reference frame will do as long as it's unaccelerated, but you need to have one. Otherwise, you're treating velocity meaninglessly. Okay, so thank you very much. I know at least what, so I actually have. So yes, thank you very much. If you have a quick question, so I'm stopping the record. So thank you very much and have a nice weekend.